All right, ladies and gentlemen, it gives me distinct pleasure to introduce today's speaker, Regina Barzilay. All I know about her is that she's a professor at MIT and a graduate of Columbia University under Cathy McEwen. And I'm sure that very soon she will need no introduction.
Thank you very much. It was short and sweet. So thank you very much for inviting me over. I really always greatly enjoy visiting Johns Hopkins and to look at the fountains in the area. Today I discovered there are many fountains on campus. This is just my personal weakness. Okay, today I'm going to talk about unsupervised multilingual learning, and this is joint work with my students Ben Snyder, Tahira, Naseem, and Jacob Eisenstein. So today, if you're going to pick up a random paper from some, computational linguistic conference, most likely it will be a paper about supervised learning, where you are given some, training data, you have annotations, for instance, parse trees, and the goal to build a model which will be able to reproduce these annotations. And for many tasks, these models are quite successful if you have, enough data to train them. However, the trouble is that we never have enough data, and for many languages, besides English, Arabic, and Chinese, we may not have any data at all. So parallel movement in the last 10 years was to look into unsupervised method, where the goal is to induce linguistic structure with no annotations whatsoever. So you can think of a very simple method like clustering. It's just one unsupervised technique. So in this case, you have lots and lots of cheap data, but the problem is performance. So for instance, for the parsing, there is a significant gap in performance between unsupervised and supervised techniques. So in my talk today, I will not try to say that I have a method which can bridge the gap between the two, but I will just try to reformulate the problem and to ask the question, can we actually learn better monolingual structure in unsupervised setting if we are learning this structure for several languages simultaneously? So at the first glance, the tasks seem much harder, because before we had just one hard problem. For English or for Chinese, we were trying to induce the structure. Now we will try to induce structure for multiple languages at the same time. But there is a lot of linguistic evidence that actually shows that it may be a good question to ask. First of all, we know that languages are related structurally. For those of you who like universal grammar, this is just one theory about this relation. There is also a lot of genetic connection between languages within the same family. But what we know as well, we know that languages have very different patterns of ambiguity. Information which is given to you for free in one language can be very confusing in another language. It could be hard to instruct this information. It can actually benefit our unsupervised learner if we put together several languages with the various patterns of ambiguity. It would just reduce overall ambiguities at present in the system. And I will show you immediately some examples. So the goal of unsupervised multilingual learning would be first to induce individual language structures and also model cross-lingual connection between the languages. So let me just throw you like a very simple example. Assume you're working on part of speech tagging and you want to decide about part of speech tag fish, which can in English be either verb or it can be a noun, correct? So if during training you are provided with the corresponding French sentences, this question gets to be much easier, because in French you have a separate word for noun fish and a separate word for verb fish. You also may have certain sort of constructural construction which would tell you that in French it's likely to be a noun in the first sentence. Like, this example doesn't advocate that French is in any way less ambiguous than English for part of speech tagging, and we can easily find examples where English can help disambiguate French. But what's interesting, there are some tasks that are really trivial for some languages and hard for others. So one example which is of such task, which is trivial for English, is a task of tokenization. So tokenization, you just want to identify separate words. If you're using spaces or you're using punctuation, it's trivial for English. Now, there is always, when I say it's trivial, there will be a person who once wrote a paper about how to do tokenization in English. And it's a WOSI task, but here you start with a baselines of 90+%. However, if you're looking at tokenization for Semitic languages or for Asian languages, it's still very hard, unsolved task, where the performance is nowhere close to 90%. Another task, which is known to be notoriously hard for English, is propositional phrase attachment, where you have a phrase, I ate pasta with cheese, where cheese is attached to pasta, but if you have I ate pasta with spaghetti, so I ate pasta with fork, then the attachment will go other way. So in this particular case, in English it's ambiguous. In Japanese you have genitive marker, which greatly reduces the ambiguity because it shows the noun attachment. And this is just few simple examples. I'm sure that if you're thinking about your native language, you would be able to come up with one task which is simple for your native language and hard for English and vice versa. And when we start to, sort of working on multilingual learning, we started looking at the literature in typology. So typology is an area of linguistics which tries to systematically characterize patterns of variation across languages. So what typologists ask is, I have many, many languages, how can I compare across them? And they develop these sort of different criteria according to which you can compare languages. So for instance, you can have subject-verb-object positioning as VO. Some languages do not satisfy this order. Or you can have number of genders, definite articles, and so on. And I just look at the typological map, I look at the number of genders, and you can get, the spectrum of variability. And you can see that number of genders can vary from none to 5 or more. It's actually interesting that most of these languages which have 5 or more genders are all geographically close in the African part of the world. Don't ask me what are the 5 genders. I didn't do proper investigation. It's something to look. So this is the name of the atlas. You can just query the web and find the information. So it's like a very big matrix with all these different questions that you can ask, and you have a language, and you can find, what values does it take for specific language. And I selected 3 languages that I happen to speak. And in this case, I look like, for instance, a definite article. You can see that in all the 3 languages, you have a very different sort of realization of articles. Okay? So, but looking at these typological tables immediately brings the following questions in mind. You have overall 4,000 languages out there, 4,000 living languages. And the question is, which languages are the best one to put together when you are trying to do multilingual learning? Do you always want to put languages which are close to you, the languages that come from the same family? Or it's like, in marriage, when you really want a couple to be very different, is it better to have very different partners together in the same group? And how do you measure what it means to be different in this case? And the other questions that you may ask, how many languages do we want to put together when we are doing unsupervised multilingual learning? Because if you look today in natural language processing, most of our multilingual models are bilingual or at most trilingual models. If you're looking at existing parallel resources, most things that were translated are translated to many, many languages, like not even Bible. Go to Dostoevsky, to any of those. If you're typically translated to many languages. So the question, is it worth for us to go through the pain to deal with this multi-parallel data, or maybe we are better just looking at 2 or 3 at a time? Why are you confused, Sanjeev?
I'm just wondering what the answer is.
Oh, we'll see the answer. We'll see the answer. But those sort of questions that I was asking myself and still asking, working on multilingual learning. So for those of you who are gonna, like Jason and some others, read the news with their laptops, let me just tell you some of our... let me just tell you sort of the main findings, what we've seen. We applied this multilingual learning to several tasks of sort of analyzing linguistic structure. So first we applied this to morphological segmentation, where you are trying to identify sort of minimal units of meaning, like in Semitic languages, for instance. And what we've seen that what we've seen in this case is that unsupervised multilingual learning actually very nicely bridges the gap between unsupervised monolingual performance and supervised performance. And we've seen the same results in the case of part of speech tagging. Again, we get some nice gains across the languages when we move from between unsupervised and supervised systems. And recently we did a work on parsing, and again we saw that multilingual learning of syntactic structure does bring the benefits. The reason I didn't put here supervised performance is because we tried it on really exotic languages. I didn't know what is the state-of-the-art performance on those languages. Okay, let me just show you another element of distraction here. So for those of you who took a class or looked some books on computational biology, you would know that in computational biology, this is considered to be state of the art to do comparative analysis. Many problems that people were unable to solve when they were looking at sort of genomic sequence of individual species were solved only when they start looking at many, many species at once. And there are sort of key problems like motif identification that are only were solved when they look at the large number of species altogether. So the question for us is what happens if you apply the same type of analysis to languages? Would you be able to get some new results? Would you be able to improve your performance on the existing tasks? So this is a slide from David Gifford, who always uses it when he tries to attract students to do computational biology. And I would like to say, obviously, we were not the first one to look at multilingual learning. The idea that languages, like looking at several languages together, can be beneficial comes from the early days of statistical natural language processing. But I guess the work which is closest to ours is the work by Dave Irowski on projection, where the idea was to use parallel data to map linguistic structure from one language to another. And the significant difference here, that in projection you actually assume that you have annotated data on one language, that you know how the structures roughly correspond between the two languages, and then you use it as a supervision for learning in a new language. What we are going to assume that we don't have structure in any of the languages, and that we don't know ahead of time how they correspond one to another. The truth is that the models that I will show you, they actually, if you do have annotation, you can use them, and they will be helpful, but this is not a requirement. And another sort of line of work which is very close to ours is the work on machine translation, where people, when they move towards more sophisticated models of linguistic structures, they're trying to model syntactic correspondences across languages. And I guess the key difference here is that we are really trying to optimize performance on the individual languages, while the goal of machine translation is to induce structure which helps to machine translation. And since the objectives are different, the underlying techniques happen to be different. I mean, I would not be surprised that there will be some synergy, but I guess we're still in early stages to see the synergy. Okay? So let me just start by showing the first multilingual model, and this is sort of a very simple model for part of speech tagging. Okay? So please feel free to interrupt me at any point. So what we will be given a parallel corpus for two languages, let's say English and French. And our goal would be to induce part of speech tags for both of these languages. Now, during training, I will assume that I have parallel corpus, but I want a model that during testing will not have parallel data. I would be able to give to it an unparalleled piece of English, and it will be able to process it. Okay? And I gave you this example about fish. It sort of shows that it may be worth to learn it jointly. So the way you typically do part of speech tagging in unsupervised fashion, you use our favorite hidden Markov model, correct? So you have a hidden Markov model where your emission probability sort of capture how likely that certain words are emitted from certain parts of speech, and you have transition probabilities which looks at the sequences of part of speech tags. So I hope at this point I don't need to remind it in more detail, but we know how to do all the parameter estimation with EM or in Bayesian framework using HMMs. So we have one HMM for English, one HMM for French. And now I will tell you how to build the structure of a graphical model which will do bilingual learning. So what I would always assume for the models that I will show you is that I am given alignment. I use GAIA or whatever your favorite alignment tool is. I know that these two words are translation one of another. Okay. So now, once I have this information, I'm going to build my first multilingual tagging model. What I'm going to do, I'm actually going to merge the aligned nodes. So now, instead of having one state for English, hidden state for English and for French, now I merge them together. So the state will be carrying two tags, one for English word and one for French word. And pay attention that I will have some nodes which are merged, but some of them will be unmerged. If there is a word in French which doesn't correspond to anything in English, it still, it stays on its own. Is it clear? So again, our HMM model would now be generating simultaneously bilingual text. It will select, one pair of tags. It will generate one word in English, one word in French, and continue this way.
Just to clarify, is that like an epsilon emission, or is it actually not modeling emission at all for Y3 there?
So we are just going to use different. So for emissions, all the emissions are monolingual. So you would have emission for English and emission for French. Now the difference would be you would have different sort of transitional probabilities. You would need to deal with it when you are doing the transitional probabilities for monolingual things, and we'll see it in a sec.
What is the order of the word changes the two languages?
We'll come back to this one. Just hold this thought. Excellent question. Let's just hold it, and we'll come back to it in 5 slides, okay? But so far, I owe you to answer the question about the change in order, but besides it, is the structure of the model... yes, another question.
So can you please explain how the merging happens when the alignments are not necessarily one-to-one?
We'll come back to this point as well when we're talking about the ordering. Okay? This is the same point. Good. But assuming that we have a very clean connection between the two languages, we can put this HMM together. And now the question, so this is our learning task. For each type of alignment, we are going to have HMM of different structure, correct? Because depending on how our alignments work together. And the goal of the learning would be actually fill in all these different tags. And the key questions that I need just to tell you is how can we do parameterization of this model? As I said to you before, emission probability are language specific. I don't need to do anything different. The question is how I'm going to deal with the transition probabilities of these merge nodes. So the first approach that we can think of is actually don't do anything special. Just assume that before you had English tag dictionary, French tag dictionary, do just Cartesian product of the two, and now you have a new set of tags, do the usual thing. But the problem with this naive parameterization is that if we are going to do it even for very small set of tags, we are really going to blow our parameter space. So if we have a trigram model and we have 13 tags, that we are going to get 13 in the forced multinomials because you're going to condition on the 4 tags, and each one of them will have 13 square parameters. But even worse, what will happen is since we have tags which participate in the merge nodes and not merge nodes, there will be no connection between the two. If you have noun which is merged and noun which is not merged, they're two independent guys. So you will have sparse counts and blown up space of parameters. So instead what we're going to do, we're actually going to factorize the conditional probabilities. And I'm showing you the case for diagram just because it's sort of easier to look at it and put it on the slide. So let me just tell you a word about the annotation. So here we have xi, which is i's tag in English, yj, which is j's tag in French, and those are 2 previous tags in English and French. And we're going to factorize it to 3 pieces. The first 2 pieces are going to look at the transitional probability in the individual languages. Because it's reasonable to assume that whatever sequences of tags you are to see in English will be very English specific. They have nothing directly to do with the patterns in French. So we can safely factorize them. But we still want this model somehow to communicate. And this is this parameter which we call the coupling parameter. A coupling parameter will make sure that if you assign a tag in English, let's say noun, you're going to assign in French something which is sort of compatible. It will hopefully rule out assignment when you have noun in English and verb in French. Okay? So this particular factorization called product of experts, because each one of these experts can rule out combinations which don't make sense. And you can normalize it and get a proper probability distribution. Okay? So now we have a model. We have our monolingual emission probabilities. We have this product of experts, which contains monolingual transition probability and coupling parameter. And we can try to estimate all these parameters using our data. So in this particular case, we decide, yes? Yeah.
You said you're explaining it for a diagram or illustrating it, but you could also do it higher order. Your coupling parameter wouldn't go to any higher order, right? Just the first two.
It will just influence the transition parameters. So in this particular case, we've selected to use, Bayesian inference to do the estimation of the parameters. There is a paper of Sharon Goldwater who did it for a normal HMM, showed that it's effective. We just did it for the bilingual case. So here our observed variables are words and alignments, and unobserved would be emission, transition, and coupling parameters. And we do sort of standard maximization of posterior probability. In the original paper, we show how you could do it with Metropolis Hastings. In our GAIA paper, which is a recent paper, we show how you can do some approximation and use Gibsonin. But it's sort of standard estimation techniques here. So now I don't want to spend a lot of time on evaluating this model because, as you will see, this is not the strongest model. But I want to bring to your attention just one fact that puzzled and fascinated me when I saw the results. So the data on which we evaluated, it's called Multext Corpus. It's a translation of 1984 to many European languages. So you can see here that there are languages from various families. So here we have Slavic representatives, primarily Slavic. Then we have Romance languages and others, okay? And I want to say that it's a different annotation scheme. It just has, roughly speaking, 14 tags, in contrast to Wall Street Journal. So now I want to show you the results for one of the languages, and I didn't select it intentionally. I could have shown you all the 8. This is the results for Serbian. And let me explain you what these results mean. So this is the result of a monolingual model. So this is the case where you can just take an HMM, remove bilingual combination, run it. You're going to get these numbers. This is the result when you are combining Serbian with Hungarian, Romanian, Slovenian, whatever, and all Czech and all other languages. So this is not an aggregate count. It's just all the bilingual models, the colorful bilingual models. Okay? So the first thing that you see here is that it doesn't matter which bilingual model you use, you always do better than the monolingual result. You always see some improvement in performance. But the fascinating part is that the improvement in performance varies greatly across the languages. You benefit for Serbian very much with English. You benefit way less if you put together Hungarian and Serbian. And when we first get these results and we saw them language per language in our training data, we thought, gosh, we would really love to explain it. Because you really want to find out who is the best partner for you, correct? Yes, do you have a question?
Is the size of the training data for all the languages nearly the same?
So, sorry?
The size of the training data for all the languages?
Yeah, it's exactly the same.
Okay.
I mean, there is some variation. It's a parallel data, yeah. I mean, there is slight variation because, maybe some languages have less auxiliaries, but it's roughly the same. It's translation. This one part is used for training, around 100,000 words. Okay?
English is the best, right? I mean,
Yeah.
Is there something to do with the fact that English is original of this work?
So first of all, there are two things that I want to say. So it's not true that for all the languages, English is the best. But there are some languages, I can't remember them on top of my head. Sometimes English is not the best partner. But I want to say something about the English part of speech tagging. Because English, in contrast to all these languages, is not morphologically rich language, and it doesn't have free order which Slavic languages exhibit, the performance on English alone is much better than performance on all these languages. So for this task, English is much easier than all the other friends. But it's not true that English always the best guy. So we spent significant amount of time and we talked to Harvard linguists trying to explain, can you tell us some linguistic theory which would tell us who is the best guy? Yes?
Before you go to the explanation, another question about anecdotal evidence. You said English is the best for Serbian and for a few other languages.
Mm-hmm.
Who is the best for English?
I think Bulgarian.
Okay, so it's not a symmetric.
It's not symmetric, definitely. Not symmetric. Okay.
So like all partnerships, who's best for you, you're not best for you.
Exactly. 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 So now, Sanjeev, I know why you're still not married. Okay. So, it's right, stay part of speech. No, this is the case. So we are not doing the cheating setup of Merialdo. We are actually not using the full part of speech dictionary. No dictionary. In this particular case, I think we just allow dictionary for words which have frequency higher than 10. So it's a reduced.
Almost every word is out of a
In a sense, you allow all possible part of speech tags, and also the performance of all these, these high numbers that we've seen for English, for part of speech tagging really doesn't translate into high numbers when we look at the languages with very good morphology, with a complex morphology such as Slavic languages. The performance, even if you do full, in the GAIA paper we have all possible experiments, so we as well have experiments of Merialdo setup, and you will see that performance of some of these languages on their own is really low, even with a full dictionary. And we ran it on some other, it's not only our model, not only our Bayesian model, we ran Stanford Target and some others. It's sort of close to state-of-the-art results. Okay, so I would tell you about experiments that we've done, like our multiple hypotheses. So first hypothesis when we submitted the paper was that it's the best to learn from within your family. And the reason that we came to this conclusion is because we started with the hypothesis that your family helps you, and we just tested it on your own family. And when the paper was accepted, we actually thought, maybe it's supposed to test in some other languages, and we thought it really doesn't work. It's not worth for you to necessarily to look at your family members. Then we did another assumption. We look at English and saw that English helps very well for some languages. We assume maybe there is one guy who is the best partner for everybody. Like in marriage, everybody needs his own. So there is no one which is optimal for all the other languages. We found two criteria which sort of correlate, exhibit mild correlation. So this sort of a cheating criteria. This is a supervised, assuming that you have your supervised data, some small amount of supervised data. Can you predict me the best partner? And the way we do it, we introduce this measure which we call cross-entropy. Let's say I give you a word in English, and I know that it is noun. Can you tell me how much uncertainty do you have about word in Hungarian? If always noun in English translates to noun in Hungarian, you don't have any uncertainty. But if it can be translated to several words, you do have some uncertainty there.
So sorry, presumably this is a negative correlation? It's low, it's a good partner, right?
Yeah. Yeah, so in this case, we saw Spearman of 0.3, which is sort of a mild correlation. Again, if you look at our MNLP paper, when we did a limited set of experiments, we strongly believe it's really a great criteria. Then we did a larger set of experiments. More languages you add, you see there is a mild correlation. Actually, the criteria which works the best is alignment density. The alignment density is something that you can compute automatically, is number of edges, aligned edges divided by the length of the sentences. And obviously, if you have very low alignment density, it pretty much means that you have two monolingual models. But if you have a very interconnected models, then you really have a lot of constraints. And in this case, sort of it's mild-high Spearman correlation. Okay, at any rate, none of these correlations that I show you are nowhere close to 1. The truth is that after a long time of checking it, we couldn't find the best partner. And then we've decided maybe the questions that we are asking is the wrong question. In contrast to Mary Sanjeev, you don't have to find here the only guy. You can be promiscuous. You can collaborate with everybody who is in your set. So then the question is, can we take everybody who is collaborating in the group and put them all together into one group? But the problem was, actually coming back to your question, is can we take our bilingual model and make it multilingual? So the first point is that you really cannot do it because of the thing what happens with reorderings. Because in this case, if you have reorderings, your graphical model is going to have a cycle. And if it's going to have a cycle, you know, some people can still, you know, continue to assume they don't have a cycle, but it's not a kosher thing to do. We don't want to do it. So what we did in our bilingual model, we actually drop all the edges which were not one-to-one and which were crossing edges. It's not too bad. You're just dropping 5% of the edges. You're still producing reasonable results. But if you're going to move to many more languages, it will not work. You're going to have really, you're going to decrease a lot of information which tells you how the assignments are constrained. So this is one problem. And another problem is the parameterization that I've shown you. So here, you see, this was our coupling parameter. So now if you have three guys, let's call it tripling parameter, see what happens. Now we have distribution over three variables, so over n variables if we want to go to n languages. So in this case, we see that the dimensionality of this distribution grows exponentially with the number of languages. And obviously, we're going to have a lot of sparse counts and other things. Yes?
So I know this isn't what you did, but one way to address this would be to factor the red term into a lot of pairwise coupling parameters.
You could do that. You could do that. But the question is if there is something beyond doing the couplings. If you want to see some patterns which actually concern several of them, do you want to do it this way? You could.
I mean, well,
I know you did. No, you could, but you know, but the hope is that there is some, whenever you're just doing it to pairs, maybe there is something which you cannot see at the pair level, but there are some patterns which you can see when you're looking at more languages, and if you're just dividing into pairs, you may lose something.
Well, what if one of the things that you were what if one of the things that you were coupling with was a latent variable? I'm just setting up.
I know, Jason. So far, you didn't ask any question, and I start to get concerned, but this is a question. Good. So that's exactly what we've done. We added a latent variable. No, Jason just told me that they read the paper during the group meeting. So the way that we are going to address it, we actually are going to add a latent variable. Let's call it Z. And we're going to add it in such a way so the assignment of tags on individual language are conditionally independent given the value of this hidden variable. So it's a very simple modification to the model. And now we can see that our coupling or tripling parameter actually very nicely decomposes to pairs where we condition on hidden variable to get tags in the individual languages. And we can see that our big formula for for transition probabilities actually nicely factorizes sort of into per language expressions. And for those of you who like to see graphical models, let me just graphically explain to you what's going on here. So we start with HMMs in our individual languages. And now, what I'm going to show is not yet a graphical model. This is a GAIA alignment. So you run your GAIA alignment, and you get alignments between nodes in individual languages. Okay. And what I'm going to do, I'm going to identify clusters of nodes which are aligned one to another. And this is the same picture where, you know, the node corresponds to one cluster of these aligned nodes. And for each one of those, I am going to get one hidden variable. So this is a hidden variable which will control the alignment of tags towards which are translation one of another. So in this clicks, yeah, it's clicks. So in this particular case, I actually simplified the story a bit. It doesn't have to be that you get these clean clicks. It may be the case that you can actually have one word controlled by two clicks. But it's exact. Everything that I'm going to tell would still apply to this model. And whenever we're looking for these clicks in practice, we don't require that every single, that everybody in the click are interconnected. We require that certain amount of them are interconnected one to another. Yeah, an almost click. Again, in GAIA paper, we have a very detailed description of exactly how it is done. Okay, so now the question is, what am I going to have in these particular nodes? What values am I going to have? So what I want these notes to tell me is what are the patterns of assignment of tags across languages. And I want to capture this multilingual context, these multilingual patterns. And what is going to be there, each one of them would contain, the values will be indexed into distribution, which is actually a set of distributions, where the set, we will have one multinomial for each language. So for instance, some value 2 may correspond to multinomial in English, French, Hebrew, and Urdu, which give higher probability to nouns. And another one with value 25 will maybe give for English and Urdu higher for adjectives, and in Hebrew it can be maybe higher for something else. Is it clear? So again, think about it for those who are not into the multinomial story. Think about it that you have just unigram models for every language on the tags. And since these unigram models can have very different probabilities, you can have an infinite number of such models, correct? So the way to deal with this whole infinite number, we can, artificially say, I don't allow infinite number. I know that there are 30 of them, and I'm just going to set it to 30. But we didn't want to make this decision since we don't know how many. And instead, we use Dirichlet process prior, which actually allows you to deal with this infinite number of values. It's a distribution of an infinite number of values, which put most of the probability on the very few patterns. That's exactly what we want to do. We want to allow any possible sort of multilingual patterns on the tags, but we know that there are some very limited number of patterns that we will actually observe in the data. And just to give you a better intuition of what's going on, I want to show you what model actually induced as the values for these superlingual tags. So in this particular case, first of all, what we've seen, and that's what we would expect, that the more languages you're going to add, the more patterns you're going to observe. And indeed, we saw that when you apply this model for 2 languages, you're going to have just 11 patterns. If you're going to move it to 8 languages, you're going to get 20. And this is an example what you're going to get for some particular value 6, for instance. You can see that Bulgarian puts probability 0.91 for noun, and for adverb it gives 0.4. So you can see that all the distribution in different languages gives some very high probabilities to nouns. However, some cases that we observed were actually not that homogeneous. We've seen some cases where in one language you give higher probability to one part of speech, and in another language you give higher probability to another part of speech. So for instance, in this case we see that Czech has higher probability for pronouns. In English, for whatever reasons, most of these pronouns were realized as determiners. And in languages such as Slovak and Serbian, it goes to verb. And the reason that it happened is because in these languages you have some construction which allows you to align verbs to take some information that you typically would express with a pronoun. So you can really see that it lends some non-trivial connection between linguistics, linguistic realization of the tags. Some of the values that you are going to get actually can be explained just by the way GAIA alignments work. So it's particularly true, this is the case of the tag 14. You would see there that if you have a language which has very few verbs, you would use light verbs to create verbs, like make announcement versus to announce. So in this case, GAIA would align the verb to the noun, and in this case, you would see that you get these tags which have some probability of nouns and verbs. Okay? So this is just some examples. So again, here we're using, standard Gibbs sampling to infer the parameters of the model. You are welcome to look at the more detailed description in the paper. And here I actually want to spend some time on evaluation and tell you what we've learned from it. So the monolingual model is just Bayesian HMM. And now we compare against bilingual model. So we can make comparison with the bilingual model in the following sense. First of all, what we can do without really working hard, we can take our bilingual model for 8 languages and just average them, correct? Average the result. Another thing that we can do, we can say, assume I have an oracle. Assume I know who is the best guy to put together in the learner. How well can I do? I don't have this knowledge during testing, but maybe I can actually combine it together. And then we have three scenarios for evaluation to show you that we are not using Marialda's setup, or just one of many. So I will show you the results for lexicon which has words higher than 5. So let me just explain you what it means. So this is the number of languages increases. So in this case, this is a monolingual baseline averaged over 8 languages. Is it clear? So just take each one of the languages, run your tagger, and average the results. This is the performance when the number of languages increases. So how we computed it, we took all possible bilingual models, took an average, all possible triples, ran an average, and so on and so forth. Took forever to run the experiment. But what you see, this is actually a very important graph, because what this graph shows to us that as you add more languages, the performance actually continue increase. So it actually motivates us to forget this very standard approach when we are taking 2 or 3 languages and do multilingual analysis. It actually shows that it's worth for us to look at more languages simultaneously. This is an average performance for a bilingual model. And again, we see the nice improvement when number of languages increases. This is performance of an oracle, when I found the best guy to combine with. And as we can see that at some point, at 7 and 8 languages, we still can do better by just doing the joint learning. And this is the breakup of the previous graph per language. And you can see that there is one exceptional guy. And the exceptional guy is English. The only language which doesn't benefit from adding more languages happen to be English. Now, I don't have a good scientific explanation why this is the case. And I will not even go into speculation, but if if we have time during question answering, maybe you may have ideas and suggestions. After multiple hypotheses, we couldn't properly demonstrate that any of them are correct. And finally, I want to show this will be maybe the last graph here. The reason that I included it, because if you look at research in machine translation, in machine translation, people typically, when they have multiple languages and they try to build machine translation system, they train bilingual models and then do some kind of voting. Correct? It's, I think, one of the Oaks papers, at least that's what he did. So we did something similar here. We train all this bilingual model, and then when I'm deciding tag, I decide in tag where the majority of them voted for it, with most votes. This is the performance of this voting thing. So you can see that it does better than the average guy, but it's nowhere close to the truly joint multilingual model. Okay, so that's pretty much what I wanted to say about multilingual part of speech tagging. And now I want to show you the slides, which for me were a revelation about asking wrong questions. So you remember when I was starting this whole discussion, I was asking, who can be the best language to pair with? And we went to linguists and asked them how to make this pairing. So and then I saw these results when we finished developing the model. So this is the performance on Bulgarian, okay, trained for the model that I showed you in the beginning when you do the merge nodes. And you can see I ordered the languages in terms of their performance, okay, so it goes as an increase. Now, I ran the superlingual model, again, on the bilingual case for Bulgarian, the second model that I showed you, and see what happens here. English, which was the best for Bulgarian previously, is now not the best, but whatever. Czech is the best for Bulgarian. So what these tables, these numbers shows, that
I missed what the connections between this and what the difference between this and
So the previous one was the one where you do the merge node, the first one that I show when you do HMM without hidden variable. This one, I took my this model with hidden variable with superlingual tags. I just applied it to 2 languages. You can apply it to 2, the same pairs. Everything is the same. And then I look at the performance. And here, I ordered the languages in terms of how much they help, so there is increase. Now I put them in the same order, and you see that whoever was the best for me for that model is not necessarily the best here. So this actually brings to my mind that the question, who is the best language, is the wrong language to ask. You should not only ask about the languages, but the models that you are using. Depending which, it actually looks very obvious, you know, insight afterwards, but at the time, it was like, oh, that you actually, if you want somehow to make languages, particular languages that you believe are good to go together, you need to have a model which will explicitly take advantage of whatever you're trying to capture. Yes?
Can you go back to 1 second? I just want to see the numbers on the y-axis. So here, English does very well, but it, you know, gets almost close to 95. And the next slide, nothing does that well. So, I mean, this suggests that the bilingual model is better if you have 2 languages. Right?
So this is, again, this is like the danger of making conclusions just looking on the slide. So our results show that on average for the full lexicon, the superlingual model does better than the, it's just sort of special case. Again, guys, yeah, it's very good. You made a proper scientific observation just based on limited data, and if I would have done a better job, I would have shown you just the ranking of usefulness, you know, averaged or something, so that we can make, but it just looks as a better picture. So the point is that it came to us later on that you really have, whenever you're asking the question, look what are the properties of your model. And now what I want to do, I want to demonstrate to you in sort of in the third part of my talk, is how can I build a model when I know that there is certain connection between languages, how can I directly exploit it in the model? If I have some small linguistic knowledge about the connection, how we can do it. And I
think you haven't answered why the multilingual hidden variable model handles the crossing.
No, so in the multilingual variable model, because you're just not going to get cycles in the structure, because you have a hidden variable, and the edges go from the hidden variable. So you can never get a cycle there.
I think the question that you might be asking is different, because this is something that I remember our reading group having to look at carefully. How do you handle divergences in order between the languages?
So in this case,
in the original example you showed for the bilingual model, all the languages, the alignments were monotonic, and that wasn't true in the multilingual model.
In this case, you don't have. I actually don't see why it would be an issue, because you're not going to have cycles, and you're going to have your transitional probabilities, which are specific per language. So
I think that's the question that he was asking. It might help to go back to that particular slide, because I think that's the point that's easy to lose.
Let me just do the following. I am afraid this is 15 minutes for me to finish the talk, so I would like to finish the talk, but I would, since we have half an hour of questions, we're going to go back and discuss it, okay? So now I want to demonstrate you sort of a different type of multilingual model so that we are not stuck on tagging all the time. I'm going to talk now about morphological segmentation.
Let me quickly make sure that I understand the connection between this graph and the previous one.
Mm-hmm.
The previous one, you had your hidden variables were pairs of tags, xi, yj. And in this one, there's a hidden variable z and there's a p of x.
No, the one I had a hidden variable. I was explicitly merging the tags together.
Right. So in some sense, your p of xy was explicit.
Yeah.
And now p of xy is factored as p of x given z, p of y
Yeah.
given z. So it's a little bit like saying instead of the joint probability matrix p of xy, you write down some sort of decomposition of it in terms of px times py, and you have z of them. So it's like a SVD of that matrix where you write it.
I wouldn't necessarily go there. And
Okay, because I think you're just getting another representation. So I'm thinking that if z, the number of values, were equal to the number of tags, then the two models are identical, because you can express any pxy as a sum of the number of px times py's. Okay, maybe I'm not saying it clearly.
So in the case for simulated models, you're right about that. There was a prior on how those latent tags are used, which controls how many they're used and what their relative probabilities are. So it's something different might actually be learned.
I think it is. Let's just take it after I finish the talk. We can discuss it in details. Okay. So now I finally want to start talking about the morphology. the point that I'm trying to make, it's not that one has some special, very special structure. The point is that what we've seen here, and we've seen with many other models, you change the model structure, all of a sudden different pairs start helping to each other. So what I want to show is, if I know something that I care about to put into my model, how I can do it explicitly and whether it helps it. So, and I'm going to do it on the task of morphological segmentation. So that's morphological segmentation, like it's important especially for Semitic languages, where you can put several sort of morphemes together to get a new word. So for instance, in Arabic, so they wrote it would be concatenated into one word, and you want to be able to divide it to pieces. Okay? So the reason is that here the multilingual learning would be of great help is because in some languages, again, spaces can unambiguously tell you where the segmentation lies. So for instance, in English, you use spaces, while in Hebrew, you're just going to concatenate the words here. And in Arabic and Hebrew, you would just put the spaces in different places. So this is the reason that, again, different patterns of ambiguity would help. But I should say that it's non-trivial to do it even if you have English, because you don't know how the Hebrew words correspond to the separate English words. This is a case where you have alignment at the word level, but you don't have alignment at the morpheme level. Another point is that what you actually want to use here explicitly is that Hebrew and Arabic come from the same Semitic family. They have a lot of more cognates. The cognates are words which sound very similar in both languages, but they're just written differently. So in this case, the word aretz and ard are two cognates. And what you want to do whenever you're doing segmentation, that the two segmentation are consistent one with another. So it will not happen that you're going to chop here AR and here you're going to chop R. Okay, so it's a very strong constraint. And what I would want to do, I would want my model to explicitly make sure that the cognates are consistently divided. And I will show you how to do it. I'm not going to get into great details about morphology, but let me just show you how you can do that. So the general structure of the model is sort of similar to part of speech tagging. You remember as we had merge and unmerge node. So here we're going to have couple morphemes and straight morphemes. Couple morphemes are morphemes which appear in all the three languages. So for instance, caliph and kelp and dog, they are translated in all the three languages, but indefinite article A just appears in English, it doesn't appear in Semitic languages. So it will be a strain morpheme. And in this particular case, the generative sketch would be the following. So what you're going to do for each bilingual phrase, you will first decide the composition of the phrase. How many morphemes are stray morphemes and how many morphemes are coupled morphemes. And you can take it from Poisson. The next one, you're going to have a joint distribution for the coupled morphemes and the distribution for strain morphemes. And then for each language separately, you're going to order the morphemes and fuse them together. So let me just briefly demonstrate. Let's say you are trying to generate this phrase other gods in English and Hebrew. So you may decide that you have three coupled morphemes for English, and in addition you're going to have one stray Hebrew morpheme. So we're going to have three boxes for this coupled morpheme, and we're going to jointly generate morphemes for English and Hebrew, and then one straight morpheme for Hebrew, and then we're going to order them and fuse them. And that's it. So the place where I'm going to be doing something to ensure that cognates are combined together is here. When I'm looking at this distribution, which governs the generation of coupled morphemes. Obviously, for English and Hebrew, I cannot do anything because they are not cognated languages. They don't come from the same family. But for Arabic and English, for Arabic and Hebrew, I actually can do that. So I want here to make sure that we are putting together morphemes which sound similar. And there are two options how to go. One way is not to care about it and just use geometric distribution as a prior. You can say, I'm going to use Dirichlet process prior for this distribution because it's a similar story. We don't know how many morphemes are out there. We can just say we're going to allow any possible lengths of a morpheme, but we're going to put all the probability mass on the few allowable. And the geometric prior would just tell if the words are close in length, then they're likely to be generated together. Instead, we're going to use actually a linguistically sort of motivated prior, which is based on probabilistic string eddy distance. And what this prior would tell me is that the words which sound similar are going to be closer and more likely to appear. So the word R and Rs to appear together would have higher probability than Kalev and Gdi, which sound very different. So you can ask me, how do you know how to build this properly probabilistic string eddy distance? And this is a place where I'm actually going to inject some linguistic knowledge. You can very easily go to any linguistic text, and it will just give you the correspondence between letters. It will tell you what are the letters within Semitic alphabets which sound very close one to another. And we build probabilistic string eddy distance so that we sort of explicitly informed it of what are the cognated letters. And I want to show you how much did it help. Let me just go to the results. So again, here you are evaluating it on F measure. You're comparing ideal segmentation against the segmentation produced by the system. So in the case of monolingual baseline, you're going to get 63.2. If you're going to do bilingual models, you immediately see improvement. So I'm going to report you the numbers on Arabic. And you see Arabic Hebrew, Arabic Aramaic, and Arabic English perform, roughly speaking, the same. And this is a geometric prior when we are looking at the lengths. Now next, what I'm going to do, I'm going to add string eddy distance prior, this linguistically motivated prior. And here we actually see that all of a sudden, we do get a boost from Semitic family. And the best results that we are getting are for Arabic and Hebrew with the string eddy prior. Okay? So the question, checking the understanding, why couldn't we apply string eddy distance for English?
It won't make any sense.
Yeah, because they're not cognated languages. There is no connection between the morphemes in the two languages. But again, this is one way how you can take a very small piece of linguistic knowledge which is out there, add to your model, and you do see the benefit. So in general, this is sort of a conclusion slide. What we've seen across all these different tasks that we applied, multilingual learning, we saw that when you're learning from multiple languages, it does help. We also saw that performance increases when you add more languages to the mixture. And we find that there is an intimate relation between the structure of the model and which languages help to each other the best. So now I have a part of the work in progress. You guys can stop me at any point, but this is something that I'm personally very excited about, so it will be hard to stop. But the reason that I included this piece is because I was hoping that we have some hard technical challenges here. And I was hoping that I would tell you what are the challenges. Maybe some people, I would be able to discuss it with you. So this part of the talk about how to do multilingual learning without parallel data, which is a very hard question, and in machine translation in particular. But the motivation to this part of the talk comes from a book that I read in 2002. This is sort of a classical book on deciphering of unknown languages. How many of you have seen this book? Yeah, so like if you have some free time, you can, I think it's really a nice read. So this book actually shows to you some examples of languages which were deciphered. They describe how people came up with insert how to decipher. And it's very interesting because some languages took like 50, 60 years to decipher. And they show you what are the scripts which are currently undeciphered and people don't know how to go about them. One interesting thing about this book, so after I read the introduction, this guy Robinson says, none of the languages which were deciphered with the computer. And then he actually goes and gives some small explanation and tells why he believes it happens, because as he says, computers do not have archaeological, historical, and cultural knowledge required to do decipherment. So when I read this particular sentence, it pissed me off badly. And I thought that we really should show that this is a wrong thing, that we should be able to do it. Because when you're looking at how people did it, and he provides very detailed explanation, you actually see that people do, what our decoders and our language model do. They sit and count and put it together, so there should be some way to do it automatically. And Kevin Knight and myself recently got a grant on deciphering, so we started doing some work. And the language that we are currently working on is called Ugaritic. And this is how the Ugaritic tablets look like. This is the word Malku, which is king in Ugaritic, so you can see the writing system. And Ugaritic was a language actually which was the first one which started the alphabet. So the tablets are from 14th and 12th BC. They were found in Syria by some peasant who was just digging. And they were deciphered. This is a deciphered language. It took 4 years to decipher it. And it was deciphered by people which were code breaker mathematicians from World War I. And they were also interested in language and new sort of Semitic philology. Again, I can tell you how they did it. A lot of counting and a lot of luck. And the way that they did deciphering, and most people do deciphering, of ancient languages, you try to find words in the close languages which would be sort of sound similar to the words in your script. You're trying to find the mapping of the alphabet which would allow you to read the cognates with similar languages. And here, actually, Ugaritic is very close to the other members of Semitic family. As you can see, that this word king sounds very similar in Arabic, Syriac, and Hebrew. So we have now, with a lot of pain, we collected the corpus of 34,000 tokens, and that's what we're using for decipherment. So in general, the way that we define the task of decipherment is, the task is the following. First of all, you want to induce alphabetic mapping between, let's say, Hebrew and Ugaritic. Second, you want to find morphological segmentation, because here again you're concatenating words together. If you're not going to do morphological segmentation, you're going to explode your vocabulary. And finally, you want to do word mapping. So if the word like king has something similar in Hebrew or in Arabic, you want to find its translation. And the only resource that we assume here is a non-parallel data in related language or languages. Okay? So we call it multilingual learning without parallel data. So what is the key linguistic intuitions that people who did decipherment manually used? The key intuition here, that the mapping between the alphabets within the families is very, very constrained. Typically one letter, like here you can see English and Arabic, that one letter in Hebrew and Arabic, in Hebrew can go at most up to 3 letters in another language. The branching factor is very low. And the insights here, again, are as follows. First of all, you assume that if you have correct alphabet mapping, you would see that letter transition would exhibit similar patterns. So for instance, human deciphers, what they did, they would say, assume this is some non-parallel data, and you see that this lowercase a always starts the beginning of the words. So you can say, in this case, capital A always starts the beginning of the word, so it means that maybe these two A's are mappings one of another. And you can say, see, the transitional probability from A to B is 2/3, and here it's also 2/3, so maybe the two are mappings of one of another. So they do it again by counting. And another idea is that you can actually see that there are mappings at the level of the units. Because many correspondences, like for instance, if you look at auxiliaries, they do change over the time. Sometimes they don't look phonetic. They change much faster than the stems. So in this case, the intuition is that you want to be able to use distributional similarity at the level of the morpheme. So if I know that these two, let's say, are cognates, and these two are cognates, D and E may not be cognates, but because they always appear in the similar distributional context of morpheme, I would say that they should be, aligned one to another. And the models that we are using, again, not very original. It's another non-parametric Bayesian model with Dirichlet process prior. So what it does, in order to capture character level regularities, we use prior, which has string eddy distance in it. And since you're going to be, since we're using the share process prior, it also identifies you these blocks of n-grams which look similar. It identifies morphemes. And we can also use distributional similarity by looking instead of one DP, we can have infinite number of DPs just conditioning on the previous morphemes. So people who are familiar with Sharon Goldwater's work on morphology, this is sort of a standard way to model context dependencies. Okay? And the general set of parameters that we are going to have separate processes, separate DPs for prefixes, stems, and suffixes, because the mappings within different parts of the word would be different. We would have, we have a distribution over stem pairs, we have separate distribution over prefix pairs, suffix pairs, and we also would have a separate language model for non-cognates. Because you would have some words which are not cognates, and hopefully language model would be able to identify them because they just select different characters. And this is a generative sketch. You flip the coin to determine whether the word was generated through the sort of family connection or it's generated independently. If it is a non-cognate, we use language-specific language model. If it is a cognate, we first draw a stem pair from stem distribution. Then conditioning on it, we are drawing prefix pair, and conditioning on a stem, we are drawing the suffix pair. This is pretty much the structure of the model. And now we assume that we observe the Ugaritic corpus. We assume that we have morphologically segmented Hebrew lexicon, and what is unobserved is alphabetic mapping, morpheme level mapping, and Ugaritic segmentation. And this is where the pain starts. So the biggest problem here that we are battling very hard is how to do inference in this model. And the reason it's so very difficult is because every single word in Ugaritic can correspond to any possible word in English, in Hebrew, and with any possible segmentation. So the space is actually tremendous. And there are some, tricks that you can use to approximate it. I can tell you about the tricks. But we've seen that the simple tricks are not doing you any good. You need something smarter. And the smarter thing that you are thinking in the direction that I would like to discuss with people who sort of look at this big search problem is how can we take advantage of the low branching factor? Because we know that the only types of mappings that we should allow between the alphabets are the ones where, Ugaritic letter goes to up to 3 English Hebrew words. So if you somehow can encode this information into a smart prior, then you could prune the search space without resorting to approximation. And that's when we are sort of currently exploring without, there is a lot to do. We are working hard on this part. So that's pretty much what I wanted to tell you about the Ugaritic, and any discussions, questions, suggestions, I would be very grateful to discuss them. And the other number that I just wanted to tell you is that if you are to try to do deciphering the way that Kevin Knight does with EM, where you just assume that mapping is hidden, this way we can recover 20 letters out of 30. And very few cognates. So it's not really a good starting point. Okay? So that's what I wanted to say. So thank you very much. Yes.
Talk to some people in the cryptography or code breaking fields to get insights into this.
So if you look today in the modern cryptography takes a very different completely different approach. Sort of cryptography that is more closer to this type of cryptography is this cryptography like, Turing time during Second World War, and the current textbooks in cryptography don't even discuss this, these issues. Now, Kevin always speculated there are some people in some agencies which have much more experience with dealing with these cryptographic problems. I don't have access to those people. But again, standard books take a very information theoretic approach to the type of code that they're considering are very different from this one, so I don't think it's very relevant.
This is a code that's meant to be broken.
Yeah.
Sure. That makes sense.
Although,
The children's supposed to learn or something.
yeah.
So I'm still bothered by why the y-axis is so low. That is, you were saying, well, in Marielle literature, sure. If I give you a dictionary, we know this kind of baseline, at least for English. If I give you a baseline, I give you where for every word, all I'm going to do is say, look it up in a dictionary and return its most likely part of speech in whatever it is, first part of speech in the dictionary. I would get about 90% right. Now you're going to say, well, I'm not going to give you a dictionary, so it's much harder than that. But I would still think that if all I was trying to learn was for each word, what is the most likely part of speech, and I'll only consider one part of speech. So I'm going to say there's no, words are not ambiguous. All I got to do is to learn for each word, what is that part of speech? And so if a word occurs in a really easy context, like after a whole bunch, I might assume it's mostly a noun. If it occurs, after a copula, almost always I might assume it's some kind of verb or something. I would think I could come very close to that baseline of 90%. Now that's, it's a broken model. It's maybe not a good model. It's very different than what we have learned, but it seems like it ought to be possible to come up with baselines that are quite a bit higher than that.
So let me actually say that the models that you are suggesting apparently happen to be very effective. So Tasker and Pereira have a paper in NIPS where what they did is sort of in a principled fashion, they enforced exactly this constraint in the posterior that you just allow every word have at most 2 tags.
Say one.
They did 2, I don't know, maybe they have evaluation with 1, but they allowed 2 tags and they were able to report on English. I don't remember if they have results for other languages, which are really very close, and I think they actually beat the Marialda setup. So it's a very good intuition.
Now, the recent Rabian network also, right? The recent work by Rabian Knight, which uses ILP to try to get sparse distributions in the direction you're talking about, which the model on the screen doesn't do at all, right?
Yeah.
The model on the screen, it doesn't have that in its prior.
Yeah, okay. So let me just make one disclaimer. And those of you who've seen best paper award and NACL for morphology see that they get, better results than we do even for the, multilingual stuff. We started with a particular models, which were state-of-the-art models for a task at a time. And the questions that we ask, if I take the model of this capacity and I make it multilingual, can you show the improvement? This is one direction of improvement. An orthogonal direction is to do better things, like to enforce that there are less tags, to make sure that you're modeling morphology.
I'm just worried that these scores are so low that it's sort of meaningless to talk about.
I wouldn't agree. I really wouldn't agree that they are so low. Yeah, I mean, this performance is actually the 2007 paper of this Bayesian HMM, which one would argue it's a reasonable one. I don't remember what will be the result if you try to do what you suggest. I don't know. But if you were to enforce these constraints for our model and for the baseline, I'm sure you can get some leverage out of it. This is the best we can do, just take the state-of-the-art model and build on top of it, since each time, every year there are better models.
Yeah, maybe there's something else that's sort of bothering Ken's intuition, I don't know. So I'm guessing if this picture is for Serbian, what would the y-axis be for English for the same picture? What would be that monolingual number?
So I don't remember, but since Ken has a computer, he can just go on my webpage. There is a GAIA page.
Latest slides, because when you had the many languages, you had the n equals 1 case, that might be the English one.
English was the case where it was the only language for which the performance dropped. As you had
Right. No, but
Yeah, but
and maybe Ken will be happy with that.
Maybe.
That
Let's
number
just.
is not 65, but 85.
No, but I mean,
There you go.
There you go. So Ken, that number is 87.
Yeah, so it's 87 for the dictionary of 5 or whatever what.
So
For when you're allowing the words of 5 or more. Marialda's setup is a very, very confusing setup. And this is a very confusing number. Because most of the words do have one single tag. So pretty much you are having your answer already given to you in training. Those account for the big part of your testing answers. And again, if you look at the...
But I mean, I've done other things where you just taking out the dictionary, it's in a whole other system, you just use the first part of speech in the dictionary, and you get numbers that better than this.
Well, but it's a different.
She's saying that the first part of speech, and it's usually the only part of speech.
Well, what I'm trying to say is from another source, and that doesn't seem to be really an unfair thing to learn. But you're saying you can't learn, I imagine you could learn that from a parametric text too. If there's only one part of speech for a word, that shouldn't be too hard to learn.
No, what I'm just saying is that if you're taking the difference that you're going so much down from the reality is because for most of the words you have already a single given tag in the training which would appear in the test.
In that case, you've got an overlap between the testing and training center. So you don't even have to cheat like that. You can still get that result. But anyway.
Another question.
Mark?
So I find your new director very interesting, but my questions are on the older stuff. The nice thing about your super tag models, now you can do all the things you want to do, but you still think that there are relationships between the language pairs or smaller groups of languages that are different than looking at everything together. So you'd imagine that rather than having one superlingual tag for everything, maybe if you have finer grained superlingual tags that only are governing a pair of language or 3 languages, that that would be better. So that suggests a hierarchy of tags instead of a single superlingual tag, and then you would want to learn what that hierarchy looks like and how to partition your data, and then you could ask. What was the optimal pair of languages for my model, and my model learned it by grouping languages in this superlingual hierarchy. I mean, it wouldn't be what are the best languages for each other, but it would be according to this model.
According to this model, yeah. But then you're coming to the question of how to learn the typology of the model, which is,
right. Well,
a hard and difficult question on its own,
right.
correct?
But my, the hope is that by getting the finer granularity, because you showed some of the superlingual tags that were clearly some languages, it was grouping verbs together, and other languages, other things were happening. And what you really like is to kind of separate those out in some way. There is some stuff on learning hierarchies. So I'm suggesting taking everything that's the most complicated and combining it so you have one more order of magnitude of complexity. Good luck.
And we know what happens exactly when you are increasing the order of complexity of these models. But again, I just want to say this is like a big disclaimer. The way that we did these superlingual models, and there are many various ways how you can go about it. And this again comes to this question: do we want to have conditional model and so on? Many things are possible and plausible. The things that I personally, I take the main lesson for me from this superlingual tag story is, that adding languages, you can do it and you can benefit from it. The particularities of the model, there are several places where you can actually do better job. Okay.
Anyone who hasn't yet asked a question?
Okay.
It's probably a pretty simple thing, but I've noticed that for Bulgarian, there's a small drop in the middle. So you have a comment?
I don't. Sorry. Oh, no. Sorry, when you look at this model, you can pay attention. The truth is, I've seen that English definitely behaves differently. And let's not forget that we are currently talking about 8 languages here, correct? And, one just can imagine how it's going to behave when we are going to add more. So again, I'm cautious to draw a lot of conclusions when we are just looking at 8 languages. We see that there is a general trend of improvement. There is one guy who doesn't like the rest, but we do need to start thinking, and there are corpora where you have really hundreds of languages. The only problem is that we don't have it annotated with parts of speech, so it will be hard to evaluate on it. But there are such corpora. The things that, again, as a disclaimer, I should say, it's very hard to take the models that I just presented and computationally scale it for work for hundreds of languages, but it's the next question. Yes, ma'am.
How did you decide the order of adding languages?
So in this stuff, what we have done, we actually, it's a good question, we didn't clarify it properly. So here what we've done, we just, for instance, for triple, we took all possible groupings of triples, and took an average. So it's the number of triples over 8, the 4, the 5, the 6. So we try all possible combinations. That's why it runs so long, this experiment. Yeah. And Jason already asked a question.
I have many questions, so I'll actually go first.
Yes.
John, go back to the slide where you have all the different languages. They're from different language families, but they're all, well, I'm not going to say what they all are because I'm going to get it wrong. I don't think they're all Indo-European, but you don't have any, you don't have Mandarin, you don't have any of the Asian languages in there. So do you have some intuition about, say, because you had said when you combine two languages and if there was a cycle, you drop them. Do you know how many cycles you would have dropped for those 8 languages versus had you added those Asian languages with some different structure?
So, first of all, yeah, we were just limited to this corpora because, to the best of my knowledge, maybe correct me if I'm wrong, this is the only part of speech tag multilingual corpus so far available. So we were limited in what we can choose. But I should say that it's true that they're Indo-European, but they do exhibit quite significant variations. For instance, Estonian and Hungarian is very different from the Slavic languages. So there is quite a big difference here. And the second point is that in this model that I present with a hidden variable, we actually do not drop anything. In the hidden variable case, whatever you get, you just add one node, and then you don't need to deal with the cycles.
Do you have some sense of the complexity, though, with different combinations of languages?
So we couldn't find any current pattern. The best thing that we could do, at least for the bilingual model, we saw that the predictor is this alignment density, which sort of shows that at least in the case when you start dropping things, or when GAIA alignment cannot find you good alignments, you are not doing great. But this is again to be expected because the model is under constraint. But it's an interesting question what will happen when you look at the very, very different pairs.
So do you think we should be putting lots of energy into these parallel corpora? Or are there
At least we can think at least a bit annotating some, maybe not building the big training resources, but at least, I think it's a big and interesting question to see what happens if you put 100 languages together and see if...
You had an entire book for this, which is a lot of words, right? And so it's one of those things where you have a fair amount of data. How much data is really necessary to do that?
Actually, we didn't do that. I don't think we did learning curve for this data. But what we did see, it's not the answer to your real question, but it's sort of the close something close. The question that, because we're pumping so much data, you could say maybe your improvement just comes because you now multiply your data by 8 rather than, using a smaller training thing. So what we've seen that this Bayesian HMM of Sharon Goldwater, if you start increasing the amount of data, the improvement that you get really levels off. You don't get a lot of leverage. And if you add the same amount of multilingual data, you do get much bigger benefit. So it's not the amount of data, but there is something in the data which helps you more. So this is indirect answer. Yeah. I'm
afraid we will close the questions because I have to get it out of here and into a plane in 5 minutes.
To Boston, yeah. Okay.
So let's